AP Chemistry. This is an overview of Unit 7 on equilibrium. This is our last unit to overview, and then we can focus in on some more specific things. So these are the topics in Unit 7. First of all, just what is equilibrium? Second is the reversible reactions. Third, what are reversible reactions and what can we see from a reversible reaction? The reaction quotient, which is Q, or the equilibrium constant, K. What is that and how do you determine it? How do you calculate the equilibrium constant? What does the size of the equilibrium constant mean? What are properties of the equilibrium constant when you have multiple steps in a reaction? How do you calculate the conditions at equilibrium? Representations of equilibrium using molecules and drawings, Le Chatelier's principle, when you add a stress to a system, and then how does that affect the reactant quotient, and then finally, when you dissolve, how is that like in equilibrium? All right, so there's a lot here, but a lot of this deals with the K value, and we will work through that. First of all, equilibrium introduction. Just some examples of things that follow equilibrium. If it's reversible, there's evaporation. Things can evaporate, and then they can condense. That is a reversible reaction. Gases can get absorbed, and then they can get released into a liquid. Things can dissolve, and then they can precipitate. So you can reverse that. Acids and bases go, especially weak acids and weak bases are reversible. Redox reactions can be reversible. And so these are all examples of reversible reactions that lead towards an equilibrium. At equilibrium, there's no observable changes. So that's what means at equilibrium, but there are dynamic processes going on at equal rates. We have the forward and we have the reverse. They are happening, but if they happen at equal rates, then it can reach an equilibrium where you don't see any changes. Graphs can show the equilibrium process, and you can look at that. For example, if I show a quick graph right here of, let's say, concentration over time, if we look at our reactants, you're going to see that they will decrease over time and eventually hit a level. If you look at your products, they are going to increase over time and eventually hit a level. When they hit a flat level, that means that they are at equilibrium. Direction and reversible reactions. So you have to understand the idea of forward and reverse. What those mean. Forward is where you go from the reactants to the products. Reverse, you go from the products to the reactants. There's a rate associated with each of these. And so understanding what that rate means. The Kc, or the K value, is how we express these things, is related to the rates of the forward over the rates of the reverse reaction, and you can understand those things. So shifts, which direction is it going to shift? Are you going to make your is the rate forward faster than the rate reverse? Then it's going to shift towards making more products. If the reverse rate is more than the forward rate, then you're going to make more reactants. If they're equal, you've reached equilibrium. So direction and shifts and rates all kind of connected together. So now we have the equilibrium constant, which is you can have a Kc or you can have a Kp. Those you do need to show clearly that you understand the difference between those when you express them. And then the reaction quotient, which is Q, which is related to K, but it's not the exact same thing. So if you have a balanced chemical equation, be able to express your Kc or your Kp value. If you remember this, if we have a coefficient A plus a coefficient on our B, and these are our reactants, but they are in a reversible reaction here, and they make our C's and our D's, as long as these are aqueous or gases, your K value, it could be Kc, you're going to use concentration, or Kp, you're going to use pressure. Your K value is going to be your your products. I'm going to do C over your reactants. So it's your concentration of C. We're using brackets for concentration, raised to whatever coefficient is on that C, times the concentration of D, which is raised to that divided by your concentration of your reactants over these things. So this main expression right here, you will be using over and over and understanding that. If it's a Kp, you're going to use pressure of C and pressure of D, and still raised to the power of the coefficient. And then you have your Q value, which is the same thing. At equilibrium, you determine this, the concentrations are at equilibrium, give you a K value. If they're not at equilibrium, then you have to express it as a Q value, your reaction quotient. If the Q value is bigger than K, then that means that things are going to shift back to the left. If your Q value is less than your K value, then it's going to shift back to the right, and if it's equal, then you're at equilibrium. And remember that solids, liquids, weak acids, weak bases are not included in the equilibrium expression. So if any of these A's, B's, C's, or D's were solids, you would not include that in your Kc value. So calculating the equilibrium constant, if you know the equilibrium concentrations, then you can calculate that using your equilibrium expression. So you just need to know what are the concentrations of your reactants, the concentrations of your products, plug them into the expression, and you can do that. You should be able to distinguish between pressure and concentration. You might want to write down the formula that we have, which I don't know off the top of my head, of how to go from pressure to concentration or vice versa, because the Kc value and the Kp value could be different numbers depending upon what you have. So calculating at equilibrium. Magnitude of the equilibrium constant. So if your K value is 1, then that means that if K is 1, then that means that it's balanced, and you're going to have your reactants and your products are going to be about the same. So your reactants and your products are going to be about the same. If your K value is bigger than 1, then that means that you are going to have more products. Okay, so you're going to have a lot more products. And if your K value is less than 1, then that means that you're going to have more of the reactants. Okay. If it's very, very large, it basically means that the reaction is going to go to completion. All the reactants are going to turn to the products. If it's very, very small, it means that it really is not going to react, and the reactants are not going to turn into the products. So understanding favored sides. If it's greater, your favored is your product side or your right side, and if it's less, then it's the opposite. All right, properties of the equilibrium constant. This is when you have multi-step processes and you would need to determine what it is. If you have your A step has a K value, so we have a value for A, and your B step has a K value, and then your C step has a K value on these. What is your overall K? Well, it depends on how you do this. So if it's a reverse, so if we want to know the B value, but we're going to reverse it, then you inverse the K. If there's a coefficient on the chemicals, then, or if you're multiplied by, like, say you need 2 A reactions to make the steps, then you need to raise it to that power. If it's 2 steps, if you're doing A and then B, then you just multiply the different K values together. So that is the different steps that you need to take. There's a lot of information here. I'm not going into much detail about these. All right, here's a big one, is using ice tables and calculating equilibrium concentrations. If you remember an ice table, you would have your, let's say we have chemical A is going to react with chemical B to produce chemical C. And then you have your initial concentrations, you have your change, and you have your equilibrium concentrations. Your K is determined by your equilibrium concentration. So this is your ice table. But you may have, if let's say you have no products to begin with and you have something, A's are going to, your reactants are going to lose, and then your products are going to gain. You have to look carefully though at the coefficients on your A's, B's, and C's and use stoichiometry. It may, like if there was a 2 in front of the C, then you would have to have plus 2x. Then you can get to your equilibrium concentrations and calculate your K. Your K is determined by your equilibrium, not by your initial concentrations. So you need to use initial conditions, use stoichiometry, that's your change, to determine your equilibrium conditions, and then use your equilibrium expression, your K expression, which is your products over your reactants, to be able to determine that. Often you'll have an unknown, and you have to solve that unknown using algebra, and sometimes even the quadratic equation. Representations of equilibrium. All right, so to be able to show equilibrium using drawings and molecules, if you have your initial conditions here, and then you have your equilibrium conditions, you should be able to show using the molecules of your reactants and your products, you should be able to show what it looks like at equilibrium. At equilibrium, you're going to have both reactants and products, depending upon stoichiometry. So if your A and B turn into 2 C's, you should have double the C's for every A that you are losing. So being able to draw the molecules in your initial and equilibrium concentrations, or halfway in between. All right, Le Chatelier's principle. So this is where we have stresses that are put onto a system that shift it either to the right or to the left. So Le Chatelier identifies stresses, how a system responds to stresses. So our stresses could include a temperature change, volume and pressure for gases, and concentration changes. Those were the ones that we focused on. Catalysts are not stresses, but they do speed up the process. Identify markers to identify the shift. So how do we know which way it shifts? Does it shift to the right or to the left? Well, you could measure pH sometimes if you have weak acids involved. If there's a temperature change, maybe you could see how exothermic or how endothermic it is. Color change is probably the big one, though. You notice a color change. If, like, say, your reactants are clear and then your products are, let's say, blue, if it is, the more blue it will get, indicates that it shifts more to the product side. The more clear it gets, it shifts more to the reactant side. So you need to be able to understand that. So with Le Chatelier's principle, these are the three things: temperature, concentration, and pressure. For concentration, if you add something to one side, it will tend to shift it to the opposite side. So the shift will be opposite of where you add it, which goes against your intuition. If you add A, you would think you would increase A, but it's the other way. If you add A, then you actually increase more products, and your shift shifts the other way. Taking away a chemical, and you can do that by maybe reacting and precipitating it, shifts it to the same side, so pulls it back. If you take away A, you actually produce more A, and you get a shift back. Temperature shifts. You have to determine whether it's endothermic and exothermic, and we talked about these. Remember, endothermic is positive H, and exothermic is negative H. So endothermic side, which way is endothermic? If you have your reactants and your products, if going forward towards the products is endothermic, then if you add heat, it's going to shift it that way. If going reverse is endothermic, then you can do that. If your H is a term, then think of that as the reactant, or that's the start, and then the endothermic direction will be in the other way. So if you have a delta H in the products, then you heat it up, it's going to shift it to the reactants. So a negative shift shifts it in the opposite direction. And then we have pressure and volume changes. If you add pressure, which is also the same thing as making it smaller. Because then by making the volume smaller, you're going to add pressure. Then it's going to shift to the side that for gases that has more bonds. So the more complex molecules, the more pressure you are, it's going to shift it that way. And then if you decrease the pressure, it's going to go the other way. All right. Your Q value and Le Chatelier. So when you add a stress, your Q changes, and it's no longer at equilibrium. Remember, Q will equal your K. At equilibrium, that's going to be happening. This is at equilibrium. If you add a stress, it's either going to change your Q or it's going to change your K. And it will force a direction shift. So if Q becomes less than K, then you're going to need to shift it to the right. If Q becomes greater than K, then you're going to need to shift it to the left. So it's connected. The Q and Le Chatelier's are connected. So you need to be able to explain that connection. Stress causes either a change in Q or a change in K. If it changes Q, like if you stress it by adding concentration, that's going to change Q. Concentration changes Q. Then you will have to recalculate your values if you add more concentration in your equilibrium expression to show that your Q is different than your K. Temperature changes K. So a higher temperature will make K depend upon which way the endothermic side is going, either greater or smaller. Okay, so rates change because of your K value. I'm going to spend a little bit of time on this. This is solubility equilibrium. So if you need to calculate the solubility of a salt, and dissolving is a soluble process. So let's say we have a chemical that is AB. I'm going to actually do this. Let's say we have a chemical that's AB2, and it's a solid. We put it into water, and it's going to dissolve in a reversible reaction so that it dissolves into A, which is aqueous, A plus, actually a 2 plus, let's say, and 2 B's minus. So this is just an example, and it could be anything that you would have. So these are both aqueous. This is solid, this is aqueous. Your equilibrium expression is given by an SP for dissolving only. So you're going to be given this solubility product. So your KSP is your products over your reactants, but the reactant is solid, and so you don't include it in there. And so the concentration is the concentration of A times the concentration of B, but since there's a coefficient on B, that one is squared. So that's your KSP. It's the same thing as all these other things, KC and KP and Qs. It's just for dissolving in specific. The concentrations that you get right here, if you plug in, if you know a KSP value, you can figure out what these concentrations are. That is called your solubility, is the maximum concentration that you can have to do this. So if it ever asked you for the solubility, then you have to figure out how much the concentration is, and then that's going to be your solubility. Okay. So dissolving is represented by KSP. Solubility is determined by the equilibrium expression. And if KSP is greater than 1, it means that it follows those rules. So if you were to solve this, you would need to use an ice table to solve this, and you may have to do that. You have your initial concentrations are 0. Your equilibrium concentrations are whatever you have here. So if I'm going to do this, we only have A's and B's, okay, in our ice table because there's no solid. The solid doesn't matter. Okay, and then we have our initial concentrations are 0, and if we in the expression that I have here, we are going to add x to this side, and we're going to add 2x to the b's because of that. That's our change. And then we have our equilibrium. Finishing our ice is just x and 2x. And so your final equilibrium expression, KSP, is what happens at equilibrium, is x times 2x, because that's our concentration of B, and that is squared. And so then you can solve this to figure out what x should be, and that is your, you can either find out what KSP is, or you can figure out what x is, and that is your solubility. So that is one of the things that you may see. And we didn't cover that very well. Common ion effect is related to this. If you have an ion that is a part of it, so let's say we are B2 is what we're looking at. That's our chemical that we're looking at. And let's say that we add a CB chemical in there. Well, we have this ion B that's part of our expression. This is your common ion right here. So that's the common ion. Common ion is the B. It's going to change how you do the equilibrium expression because you already have some of the ion that you have in these other things. So your solubility changes if you already have some ions in there that are a part of the chemical that you're trying to dissolve. So you would have to add, you think about this as in terms of Le Chatelier's principle. So if we did this AB2 equilibrium with A plus and 2B minus, okay. If we add some B's, it's going to shift towards the other side. So if we add some B's by adding the CB in here, if we do that and we shift it to the other side, that means that we are going to produce more solid and not as much is going to dissolve. Oh. I lost that. Okay, so if we add B to this, then that's the common ion in the CB, then it's going to shift it the other way. All right, and pH and solubility. So this is affected by weak acids and weak bases that you would have. So what's the quality? This is no calculations in this, but qualitatively, what happens when you dissolve a salt that's part of a weak acid or weak base? So for example, let's take a look at our acetate, acetic acid, which is vinegar. Okay, very common one that you have. So this is our acetic acid. The ion right here, acetate, let's say that we put sodium acetate into the solution. Well, sodium acetate, this is your acid right here, but it has a conjugate base, which is C2H3O2 minus. That's your acetate ion is the base. So this is your acid-base pairs, if we remember from talking about that. If you add an ion that has your conjugate base in there, then that's going to affect the pH changes with that. And you just can think about that in terms of Le Chatelier's principle. All right, if you add more of this, it's going to shift it this way, which is going to make it, let's add our, if you add more of the conjugate, then it's going to shift it the opposite direction. We'll shift it this way, which is going to lose H+, which will raise your pH. So just to be able to describe that whole process there with pH and solubility. All right, that's it. We will do some example problems in class, but hopefully at least that gave a refresher of solubility.